the universe contains structures so large that even the most careful comparisons begin to fail. We can build ladders of scale, moving from the familiar to the distant, and still discover that those ladders end abruptly in places we did not expect. The story that follows begins with something that feels enormous to us, and then gradually moves outward until that sense of scale quietly breaks. There is a galaxy more than 1 billion light-years away, whose size stretches beyond what most people imagine a galaxy could be. It did not appear dramatic when astronomers first catalogued it. Through a telescope, it looked like a faint patch of light, no brighter than many others scattered across deep sky images. Only later did careful measurements reveal that this dim blur belonged to one of the largest galaxies ever discovered. Before we reach that distant system, it helps to begin somewhere our intuition can still stand. Human minds do not naturally grasp millions of light years or trillions of stars. We understand size through objects that exist close to home, through the physical scales of planets, stars, and the galaxy we live in. By climbing outward step by step, the shape of the larger structure becomes easier to see. Our journey will move through 3 stages. First, we will build a sense of cosmic scale, starting from the Earth and expanding outward until galaxies themselves become the basic units of the story. Second, we will look at the environment where the largest galaxies grow, places where gravity gathers enormous amounts of matter over billions of years. And finally, we will arrive at a particular giant galaxy, a system so large that it reshapes our sense of what the universe can assemble. The Earth is a natural place to begin. From the surface of our planet, the horizon curves gently away in every direction. Oceans stretch for thousands of miles, and mountain ranges rise into thin air high above the ground. For everyday human experience, the planet already feels immense. Yet this scale is only the first small step in a much larger ladder. Once we leave the Earth behind and look upward, the next anchor of scale appears immediately. The Sun dominates our sky and governs the motion of every object in the solar system. Its gravity holds planets, moons, asteroids, and comets in orbit, shaping the quiet architecture of our local cosmic neighborhood. Even so, the Sun itself is not exceptional. It is a typical star, one among hundreds of billions scattered through the galaxy we call home. The Milky Way is the next step in the ladder, and its scale pushes human intuition further than most everyday comparisons can follow. Seen from Earth on a dark night, the Milky Way appears as a faint, luminous band stretching across the sky. That hazy strip is not a cloud or a glowing mist. It is the combined light of distant stars packed so densely along the plane of our galaxy that their individual points blend together into a continuous river of light. For most of human history, that river marked the boundary of the known universe. Ancient observers imagined it as spilled milk across the heavens, or as a celestial pathway crossing the night. Only in the last century did astronomers discover that the Milky Way is not the entire universe, but merely one galaxy among many. Beyond it lie billions of others, each carrying its own population of stars and planets. Some resemble our galaxy, with graceful spiral arms and rotating disks. Others are smaller and irregular, distorted by gravitational encounters with their neighbors. And in certain rare places, galaxies grow far beyond the ordinary scale we see nearby. One of those rare places is where our story eventually leads. But first, the ladder of scale must begin. Start with the Earth again, because it remains the only cosmic scale we experience directly. Continents span thousands of miles, oceans cover most of the surface, and the atmosphere rises far above the ground before fading into space. Standing on the planet's surface, it is easy to feel that the world itself is vast. Yet the Earth is small when placed beside the Sunday. The Sun contains almost all the mass in the solar system, and its gravity quietly directs the motion of every planet that circles it. If the Earth were reduced to the size of a marble, the Sun would still appear as a large sphere many feet across. This difference in scale is not immediately obvious from daily life. The Sun appears in the sky as a bright disk, while the Earth beneath our feet seems endless. Only when measurements are made, and the distances of space are considered carefully, does the imbalance become clear. The Sun is more than 1 million times the volume of Earth. It is a sphere of hot plasma large enough that over 1 million Earth-sized worlds could fit inside it. This comparison already stretches ordinary intuition. Yet the Sun is not the largest kind of star that exists. Across the galaxy, there are stars much larger and more luminous. Some swell so greatly that if they replaced our Sun, their outer layers would extend beyond the orbit of Mars. A few grow even farther outward, reaching distances that would approach the orbit of Jupiter if placed within our solar system. These stellar giants remind us that the Sun's dominance in our sky does not mean it is an extreme object in the universe. It is simply the star closest to us. Distance and familiarity shape our perception of scale more than the true sizes of cosmic objects. Once this realization settles in, the next step in the ladder becomes easier to imagine. The Sun is only one star among many. Our galaxy contains hundreds of billions of stars scattered across a vast rotating disk. Each of those stars occupies its own region of space, often surrounded by planets, moons, and clouds of gas and dust. When astronomers describe the Milky Way, they are not referring to a single object like the Sun or the Earth. They are describing a structure composed of enormous numbers of stars, moving together through space under the influence of gravity. Understanding that structure requires stepping back even further from the familiar scales of planets and stars. The solar system is small, the Sun is large, but the galaxy that holds both of them is larger still. The Milky Way is a spiral galaxy, a rotating system where stars, gas, and dark matter gather into a flattened disk with curving arms that wrap gently around the center. From above, the structure would resemble a vast pinwheel slowly turning in the darkness of space. Seen from within, however, its shape is much harder to perceive. Our solar system sits partway out along one of the spiral arms, embedded among countless other stars. From this vantage point, we cannot look down upon the galaxy the way astronomers view distant galaxies through telescopes. Instead, we see the Milky Way from the inside. On clear nights away from city lights, the galaxy reveals itself as a faint, luminous band crossing the sky. That pale glow is produced by distant stars whose light merges together along the dense plane of the galactic disk. Each point of light in that band represents a star separated from its neighbors by enormous distances. The Milky Way stretches across roughly 100,000 light-years. A light-year is the distance light travels in a year, moving at about 300,000 kilometers every second. Even at that extraordinary speed, a beam of light would need 100,000 years to travel from one side of the Milky Way to the other. This comparison introduces an unusual connection between astronomy and human history. Modern humans have existed for only a few 100,000 years. If a beam of light began crossing the galaxy when the earliest members of our species appeared, it would still be traveling today. Inside that enormous span of space reside hundreds of billions of stars. Around many of them orbit planets, and around those planets orbit moons. Vast clouds of gas drift between the stars, forming new stellar systems when gravity causes them to collapse. The Milky Way therefore functions less like a single object and more like a city of stars. Each star system occupies its own neighborhood, separated from the next by distances far greater than anything within our solar system. Travel between them would require journeys lasting many thousands of years, even at speeds far beyond current technology. Despite its immense scale, the Milky Way is not unusual among galaxies. When astronomers observe the distant universe, they find systems similar in size and structure, scattered across the sky. Some are slightly larger, some slightly smaller, but the Milky Way fits comfortably within the typical range of spiral galaxies. One of those nearby neighbors is the Andromeda galaxy. Located about 2.5 million light-years away, Andromeda appears in dark skies as a faint, elongated smudge visible to the naked eye. That dim patch of light represents an entire galaxy containing perhaps 1 trillion stars. The realization that Andromeda is another galaxy was once revolutionary. For centuries, astronomers debated whether such faint smudges in the sky were clouds within our own galaxy or distant systems of stars beyond it. In the early 20th century, careful measurements settled the question. Those hazy patches were not nearby objects at all. They were galaxies in their own right, separated from the Milky Way by millions of light-years. With that discovery, the scale of the universe expanded dramatically. Our galaxy was no longer the whole cosmos. It was only one island of stars among many. Once astronomers understood that galaxies existed beyond the Milky Way, the next step was to determine how many of them filled the observable universe. Early observations revealed dozens. Later surveys discovered thousands, then millions. Modern estimates suggest that the observable universe may contain trillions of galaxies. Each of these systems carries its own stars, planets, and interstellar clouds. Many are small dwarf galaxies with only a few billion stars, while others rival or exceed the Milky Way in size. Despite this diversity, galaxies rarely exist in complete isolation. Gravity causes them to gather together into groups and clusters. Our own galaxy belongs to a modest collection known as the Local Group, which contains the Milky Way, Andromeda, and several dozen smaller galaxies bound together by mutual gravity. These groups are not the largest structures in the universe, Galaxy groups themselves often belong to larger clusters containing hundreds or even thousands of galaxies. Within these clusters, galaxies drift slowly around a shared center of gravity, sometimes passing close enough to interact or merge. When astronomers map the distribution of galaxies on the largest scales, a striking pattern emerges. Galaxies do not fill space evenly. Instead, they trace out enormous filaments and sheets, forming a vast network sometimes called the cosmic web. Along these glowing threads lie the densest concentrations of matter. Galaxy clusters sit like bright knots where several filaments intersect, while vast empty regions known as cosmic voids occupy the spaces between them. If the universe could be viewed from a sufficiently distant vantage point, it would resemble a three-dimensional web of light. Within this web, gravity continues to pull matter together. Small galaxies merge into larger ones, and groups of galaxies gradually drift toward the densest parts of the network. Over billions of years, these processes reshape the population of galaxies. Some galaxies remain relatively small, quietly orbiting within clusters without undergoing major changes. Others experience repeated encounters with neighbors, colliding and merging until their original structures dissolve. Each merger adds mass and stars to the growing system. Through this slow accumulation, a few galaxies grow far beyond the ordinary range of size. These giants usually reside near the centers of rich galaxy clusters, where gravity gathers matter from many directions. Over time, they absorb smaller galaxies that wander too close. The process unfolds on timescales so long that it defies ordinary intuition. A single galactic merger can take hundreds of millions of years. Tidal forces stretch the galaxies into long arcs of stars before they finally blend into a single, larger structure. When astronomers study clusters of galaxies today, they often find one central galaxy that stands apart from the rest. These central systems are typically larger and more massive than their neighbors, reflecting a long history of mergers and gravitational growth. Most of them remain within the expected range of galactic size. But in a few rare clusters, the central galaxy becomes something much larger. To understand how the largest galaxies form, it helps to imagine gravity shaping the universe like a landscape. In this landscape, some regions resemble hills, while others resemble valleys where matter naturally gathers. Galaxy clusters occupy the deepest valleys in this cosmic terrain. Their gravity pulls surrounding galaxies inward, gradually concentrating enormous amounts of matter into a relatively small region of space. Over billions of years, these valleys become crowded with galaxies orbiting one another. Near the center of such a cluster, gravity becomes especially strong. Galaxies that drift toward the center lose energy through repeated interactions with their neighbors and through the influence of the cluster's massive dark matter halo. As a result, they spiral slowly inward. When two galaxies pass close to each other under these conditions, their mutual gravity distorts their shapes. Long streams of stars stretch outward in curved arcs, and clouds of gas compress as the galaxies begin a gradual dance around one another. Eventually, they merge. During these mergers, the individual stars rarely collide directly. The distances between stars are so large that most pass one another without contact. Instead, gravity reshapes the orbits of the stars, redistributing them into new patterns that form a larger galaxy. Gas clouds behave differently. When gas from two galaxies collides, it compresses and heats, sometimes triggering bursts of new star formation. These energetic episodes illuminate the merging system and alter its structure further. After many such encounters, the orderly spiral arms that once defined the original galaxies disappear. The remaining stars settle into a smoother, rounder configuration known as an elliptical galaxy. This form often marks the end stage of repeated galactic mergers. The largest elliptical galaxies usually occupy the centers of massive clusters. Their size reflects the long history of smaller galaxies that have gradually been absorbed into them. Each merger leaves traces in the motions and chemical composition of the stars now bound to the larger system. Astronomers sometimes refer to this process informally as galactic cannibalism. The term sounds dramatic, but the mechanism behind it is simple. Gravity pulls matter together, and over long spans of time, that attraction reshapes entire populations of galaxies. Most clusters contain a central galaxy that has grown in this way. It sits at the bottom of the gravitational valley, slowly gathering mass from its surroundings as smaller galaxies drift inward. Occasionally, the process continues far longer than usual. In those rare environments, a galaxy can grow to extraordinary size. One such giant lies more than 1 billion light-years away, in a cluster known as Abell 2029. At the center of that cluster sits a galaxy whose scale stretches far beyond the Milky Way. If exploring the true scale of the universe interests you, you can subscribe to follow future journeys like this. New videos continue examining the structures that shape the cosmos, one discovery at a time. Now, to understand how a galaxy like this can exist, we first need to climb the ladder of cosmic scale. To reach it, however, we first need to understand how mergers build galaxies layer by layer across cosmic time. The next step in the story moves deeper into that process. If you want, I can continue immediately with Cluster B formation, plus reveal to 3,400 words, where the script will introduce galactic mergers in detail and reveal IC 1101. The largest galaxies in the universe do not appear randomly. They form in environments where gravity has been quietly collecting matter for immense stretches of time. These places are typically found at the centers of galaxy clusters, where the gravitational landscape creates a natural gathering point for surrounding material. A useful way to imagine this environment is as a broad valley carved into the structure of the universe. In this valley, gravity gently pulls galaxies inward over billions of years. Some galaxies orbit within the cluster for long periods, but others gradually lose energy through repeated gravitational interactions. As they lose that energy, their paths change. Instead of remaining in wide orbits around the cluster, they begin to drift closer to the center. Each slow inward motion brings them nearer to the region where the cluster's gravitational pull is strongest. At the center of this gravitational valley, something remarkable begins to happen. Galaxies that wander too close no longer remain separate systems forever. Their stars, gas, and dark matter begin interacting with the central galaxy in ways that slowly reshape both structures. This process unfolds so gradually that it rarely appears dramatic in a single moment. Instead, it resembles a long historical accumulation. One galaxy merges with another. Later, a third galaxy drifts inward and becomes part of the growing structure. Over time, the central galaxy becomes larger and more massive. Its halo expands. Its population of stars grows. What once may have been an ordinary galaxy slowly transforms into something far more substantial. Clusters provide the perfect environment for this growth because they contain so many galaxies moving through the same region of space. Every orbit around the cluster center brings galaxies into closer contact with one another. Some pass by with little change. Others experience stronger gravitational encounters that distort their shapes and alter their motion. In certain cases, these encounters lead to mergers that permanently combine two galaxies into one. The central galaxy benefits from these interactions more than any other object in the cluster. Because it sits at the deepest part of the gravitational valley, it becomes the natural destination for many of the galaxies that drift inward. With each merger, its structure grows more complex. Stars from the absorbed galaxies disperse into new orbits. Gas clouds mix and compress. The central region accumulates increasing amounts of mass. This process can continue for billions of years. The cluster steadily feeds its central galaxy with new material, adding layer after layer of stellar history. Each absorbed galaxy leaves traces in the motions of stars and in the chemical composition of the larger system. Astronomers studying these giant galaxies often describe them as archives of cosmic evolution. Their stars formed in many different environments, long before becoming part of the same structure. When those stars are examined carefully, they reveal the story of the galaxies that once existed independently. In most clusters, the growth eventually slows. The central galaxy becomes large, but remains within the typical scale astronomers expect for elliptical galaxies. In a few rare clusters, however, the process continues much further. Those clusters produce galaxies whose size stretches far beyond the familiar range. The mechanism that allows galaxies to grow is known as galactic merging. It occurs when two galaxies pass close enough that their mutual gravity begins to alter their shapes and motions. Unlike collisions between solid objects, these encounters unfold across enormous distances and timescales. A typical galaxy contains hundreds of billions of stars, yet the distances between those stars are so vast that direct stellar collisions are extremely rare. When galaxies merge, the stars themselves mostly pass by one another without contact. The real interaction happens through gravity. As the galaxies approach each other, tidal forces begin stretching their structures. Spiral arms distort. Long arcs of stars extend outward into space, forming luminous streams that can span hundreds of thousands of light years. These tidal features are one of the first visible signs that a merger has begun. They reveal how strongly gravity can reshape entire galaxies when two massive systems move close together. Gas behaves differently from stars during these encounters. When clouds of interstellar gas from two galaxies collide, they compress and heat. This compression can trigger bursts of star formation, producing clusters of bright young stars that briefly illuminate the merging system. Meanwhile, the stars themselves follow complex new paths, determined by the changing gravitational environment. Instead of remaining in orderly orbits within a spiral disk, they scatter into a wide range of trajectories. Over time, these scattered orbits settle into a more spherical arrangement. The graceful spiral pattern that once defined each galaxy gradually disappears. In its place emerges a smoother, rounder structure known as an elliptical galaxy. This transformation can take hundreds of millions of years. At first, the two galaxies appear tangled together, their spiral arms twisted into long filaments. Later, the stellar motions become more chaotic as gravity redistributes their energy. Eventually, the system relaxes into a new equilibrium. The stars settle into stable orbits within a single larger galaxy whose shape no longer resembles the original spirals. During this long process, another transformation occurs deep in the center of the merging galaxies. Most large galaxies contain supermassive black holes at their cores. When two galaxies merge, those black holes gradually move toward the center of the newly forming galaxy. At first, they orbit each other at large distances. Over time, their orbit shrinks as gravitational interactions with surrounding stars and gas remove energy from the system. Eventually, the two black holes merge, producing a single, more massive black hole. These mergers release energy in the form of gravitational waves, ripples in space-time that travel outward at the speed of light. Although the waves themselves are invisible, their effects can be detected with specialized observatories designed to measure tiny distortions in space-time. Thus, the merging of galaxies reshapes not only the visible structure of stars and gas, but also the hidden architecture of gravity itself. In clusters where many galaxies drift toward the same center, this process repeats again and again. Each merger adds more stars to the central system. Each encounter redistributes the orbits of those stars and contributes to the gradual growth of the galaxy. Over billions of years, dozens of mergers may occur within the same cluster center. Smaller galaxies disappear into the expanding structure of the central giant. The result is a galaxy whose history is written in layers. Some stars formed billions of years ago in distant systems that no longer exist as independent galaxies. Others formed later, triggered by the compression of gas during mergers. When astronomers examine such galaxies today, they see not a single unified creation, but a structure assembled from many different origins. The stars belong to one galaxy now, but they were not all born together. This slow accumulation is the key to understanding the largest galaxies in the universe. They are not sudden creations. They are the long-term result of gravity gathering matter over cosmic time. More than 1 billion light-years from Earth lies a galaxy cluster known as Abell 2029. From a distance, it appears as a dense concentration of faint galaxies scattered across a small region of the sky. Each of those galaxies contains billions of stars, yet at this distance they appear as tiny smudges of light. Clusters like Abell 2029 are among the largest gravitationally bound structures in the universe. Hundreds of galaxies move slowly within the cluster's enormous halo of dark matter, orbiting around a shared center of gravity. The space between the galaxies is not empty. It contains extremely hot gas, heated to millions of degrees by the gravitational energy of the cluster. This gas emits X-rays that astronomers can detect with space telescopes, allowing them to map the structure of the cluster in detail. At the center of Abell 2029 sits a galaxy that stands apart from the others. Even in early photographic surveys, it appeared slightly larger and brighter than its neighbors. At first, there was little reason to suspect that it was anything extraordinary. The galaxy was catalogued under the designation IC 1101. Like many astronomical objects, its name reflects the order in which it was recorded, rather than any distinctive property of the system itself. Only later did astronomers begin to realize that IC 1101 was unusual. When they measured its size and luminosity more carefully, the galaxy revealed dimensions far larger than those of most known galaxies. The cluster environment surrounding it provided an important clue. As the central galaxy of a massive cluster, IC 1101 occupied the deepest part of the gravitational valley we described earlier. Over billions of years, it had been positioned perfectly to accumulate matter from its surroundings. Galaxies drifting through the cluster occasionally passed close to the center. When they did, gravitational forces gradually stripped stars and gas from those systems, adding them to the growing structure of the central galaxy. Some of those galaxies likely merged completely with IC 1101. Others were torn apart more slowly, leaving streams of stars that eventually dispersed into the outer halo of the larger system. From a distance, the result appears calm and smooth. The galaxy's light spreads outward in a gentle elliptical glow, without the bright spiral arms seen in galaxies like the Milky Way. Yet beneath that smooth appearance lies a history of repeated mergers and gravitational encounters. Each absorbed galaxy contributed new stars to the system. Each merger increased the mass of the central galaxy and expanded its gravitational influence within the cluster. Over billions of years, this steady accumulation transformed IC 1101 into something far larger than most galaxies. The full scale of that transformation becomes clear when its dimensions are compared with those of more familiar galaxies. The Milky Way, our home galaxy, spans roughly 100,000 light-years from one side to the other. Within that vast disk lie hundreds of billions of stars, including the Sun and the planetary system surrounding it. Even this immense scale can be difficult to visualize. Yet compared with the galaxy at the center of Abell 2029, the Milky Way begins to look small. IC 1101 stretches across a region estimated to be between 4 and 6 million light-years in diameter. This means that its visible structure extends dozens of times farther than the disk of the Milky Way. To appreciate the difference, imagine reducing the Milky Way to the size of a small coin. In that same comparison, IC 1101 would span the length of a large room. The familiar scale of our galaxy becomes only a small reference point within the much larger structure. The size difference becomes even more striking when the galaxies in our local cosmic neighborhood are considered together. The Milky Way is not alone in its region of space. Nearby lies the Andromeda Galaxy, slightly larger than our own, along with dozens of smaller galaxies that form the local group. This entire collection of galaxies occupies a region only a few million light-years across. If IC 1101 were placed where the Milky Way currently sits, much of the local group could fit comfortably within its extended structure. In other words, the largest galaxy we have discovered is not merely larger than the Milky Way. It approaches the scale of the entire environment in which our galaxy resides. Such comparisons reveal how easily our sense of cosmic scale can shift when new observations appear. Objects that once seemed enormous can become modest reference points once something larger is discovered. Yet, size alone does not fully describe the magnitude of IC 1101. Its enormous dimensions are matched by an equally remarkable population of stars. Astronomers estimate that the galaxy may contain on the order of 100 trillion stars. This number is difficult to imagine directly. If someone attempted to count those stars one by one at a rate of 1 star per second, the task would require millions of years. Despite this immense population, the galaxy does not appear dramatically brighter than others at similar distances. Many of its stars are old and relatively faint compared with the brilliant blue stars found in younger galaxies. This suggests that much of the galaxy's star formation occurred long ago, during earlier stages of its growth. As the supply of cold gas diminished over time, the rate of new star formation gradually declined. Today, IC 1101 appears as a vast elliptical system composed primarily of older stars. Its light spreads outward in a smooth halo that fades slowly into the surrounding darkness of space. The calm appearance of the galaxy hides the turbulent history that created it. Each star within its enormous structure carries a record of the mergers and interactions that shaped the galaxy over billions of years. The scale of this system raises an important question: how did the universe assemble something so large? The answer lies not only in the visible stars, but also in deeper processes that operate within galaxy clusters. To understand the scale of IC 1101 more intuitively, it helps to imagine what would happen if the galaxy occupied the place of the Milky Way in our cosmic neighborhood. In that scenario, the solar system would still orbit a star located somewhere within the galaxy's enormous stellar population. From the perspective of our planet, the night sky might look quite different. Instead of seeing a relatively narrow band of stars forming the Milky Way across the sky, observers might see a far broader glow stretching in many directions. The dense population of stars within the galaxy's central regions would produce a luminous background far brighter than the one we see today. The distances between stars near our location might remain similar to those within the Milky Way. Even in very large galaxies, stars are typically separated by vast expanses of space, but the overall scale of the system surrounding us would be dramatically larger. Travel across the galaxy would require journeys lasting millions of years, even at the speed of light. Messages sent from one side of the galaxy to the other would not arrive for several million years, and any reply would require the same length of time to return. Communication across such distances would unfold on timescales comparable to geological eras on Earth. The presence of neighboring galaxies would also appear different. Instead of occupying a region comparable to the diameter of the Milky Way, nearby galaxies might seem relatively close within the larger structure of IC 1101. Andromeda, for example, could lie well within the extended halo of the giant galaxy rather than existing as a separate system. Smaller galaxies that now orbit the Milky Way might instead appear as satellite structures embedded within the outer regions of the larger galaxy. This perspective highlights how dramatically the scale of a galaxy can influence the environment surrounding its stars. Despite these differences, the fundamental physical laws governing the galaxy would remain the same. Gravity would still control the motion of stars and gas. Stellar evolution would continue producing new generations of stars from collapsing clouds of interstellar material, although at a slower rate in such an old system. At the center of the galaxy, another powerful influence would dominate the dynamics of the inner regions. Like most large galaxies, IC 1101 contains a supermassive black hole at its core. The growth of that black hole is closely tied to the history of mergers that built the galaxy itself. Understanding that connection reveals yet another layer of structure hidden within the giant galaxy. The next step in the story moves inward toward that central region where gravity reaches its most intense form. If you'd like, I can continue immediately with Cluster C Deep Physics to 3,200 words, covering 100 trillion star population in detail, central supermassive black hole, dark matter halo, cosmic web feeding structure. This is the section where the script becomes most scientifically dense but still calm, QSJ narration. When astronomers estimate the stellar population of IC 1101, the numbers become difficult to grasp in ordinary terms. The galaxy may contain on the order of 100 trillion stars. This number is not exact, because counting individual stars at such distances is impossible. Instead, scientists infer the population by measuring the total light emitted by the galaxy and comparing it with the brightness of known stellar populations. Even as an estimate, the number reveals something important about the scale of the system. 100 trillion stars represent hundreds of times the stellar population of the Milky Way. Each one of those stars follows its own orbit through the galaxy, influenced by the combined gravity of the entire structure. Despite this immense number of stars, IC 1101 does not appear unusually bright when compared with some smaller galaxies. The reason lies in the types of stars that dominate its population. Many of the stars in this galaxy are old. Young galaxies often shine with brilliant blue stars that burn their nuclear fuel quickly and intensely. These stars are massive and luminous, but they live only a few million years before ending their lives in supernova explosions. Their presence gives young galaxies a bright, energetic appearance. In older galaxies, most of those massive blue stars have already disappeared. What remains are smaller, longer-lived stars that burn their fuel slowly. These stars emit softer light, often appearing redder in color. Elliptical galaxies, such as IC 1101, typically contain large populations of these older stars. Over billions of years, repeated mergers consumed much of the cold gas that might otherwise have formed new generations of stars. Without abundant gas clouds collapsing into new stars, the galaxy gradually entered a quieter stage of stellar evolution. The stars that remain continue to orbit through the galaxy in complex paths. In spiral galaxies like the Milky Way, stars move mostly within a rotating disk. In elliptical galaxies, the orbits are far more varied. Some stars travel in elongated paths that carry them deep into the center before swinging outward again. Others move along orbits that tilt above and below the galaxy's main plane. The result is a smooth, rounded structure where stars occupy many different orientations. From a distance, this mixture of orbits produces the gentle glow characteristic of elliptical galaxies. The light spreads evenly in all directions without the bright spiral patterns seen in younger systems. Each star within this vast population carries a chemical fingerprint that reveals its origin. By studying these chemical signatures, astronomers can determine whether groups of stars formed in the same environment long ago. In massive galaxies like IC 1101, those signatures often show remarkable diversity. Some stars formed early in the universe, while others formed later during mergers that compressed gas clouds into new stellar clusters. Together, they form a population that records the entire history of the galaxy's growth. At the center of nearly every large galaxy lies a supermassive black hole. These objects contain enormous amounts of mass compressed into extremely small regions of space. The Milky Way itself hosts such a black hole, known as Sagittarius A*, whose mass is about 4 million times that of the Sunday. Even this mass is difficult to imagine. A region smaller than our solar system contains millions of solar masses bound together by gravity so intense that not even light can escape once it crosses the event horizon. In the case of IC 1101, the central black hole is believed to be far more massive. Astronomers estimate that it may contain tens of billions of solar masses. Some measurements suggest values between 40 and 100 billion times the mass of the Sunday. This extraordinary mass did not appear suddenly. Like the galaxy surrounding it, the black hole likely grew through a long history of mergers. When two galaxies collide, their central black holes begin orbiting each other within the newly formed galaxy. At first, the distance between them may be enormous by human standards, but gravitational interactions with surrounding stars slowly reduce their separation. As the orbit shrinks, the two black holes eventually form a tightly bound pair. At this stage, their motion produces gravitational waves that carry energy away from the system. Those waves propagate through space-time itself, gradually drawing the black holes closer together. When they finally merge, the result is a single black hole with greater mass than either of the original pair. The merger releases a burst of gravitational energy that travels across the universe as ripples in space-time. In clusters where galaxies merge repeatedly, this process can occur many times. Each merger adds more mass to the central black hole, allowing it to grow alongside the galaxy that surrounds it. During certain phases of its growth, a supermassive black hole can become extremely active. Gas falling toward the event horizon forms a rapidly rotating disk known as an accretion disk. Friction within this disk heats the gas to enormous temperatures, causing it to emit intense radiation. In some cases, the energy released by the disk drives powerful jets of particles outward from the poles of the black hole. These jets can extend for millions of light years, carving enormous cavities into the surrounding gas of the galaxy cluster. Observations of clusters similar to Abell 2029 often reveal these cavities in the hot gas surrounding the central galaxy. They appear as large bubbles where the jets from the black hole have displaced the surrounding material. Such events can influence the entire galaxy. The energy released by the black hole can heat gas that would otherwise cool and collapse into new stars. In this way, the black hole helps regulate the growth of the galaxy itself. Today, the central black hole in IC 1101 appears relatively quiet. The galaxy contains little cold gas to feed an active accretion disk, and the dramatic jets associated with active galaxies are not prominent. Nevertheless, the black hole remains the gravitational anchor of the galaxy's core. Its immense mass influences the motion of stars within the inner regions of the galaxy. Even though it occupies only a tiny fraction of the galaxy's total volume, its presence reflects the long chain of mergers that shaped the galaxy over billions of years. Studying an object as distant as IC 1101 requires methods that extend far beyond simple observation. Astronomers cannot travel to the galaxy or observe its stars individually. Instead, they rely on subtle measurements of light and motion to reconstruct its properties. One of the most important tools is spectroscopy, the study of how light spreads into different wavelengths. When starlight from a distant galaxy passes through a spectrograph, it separates into a spectrum that reveals the chemical composition of the stars producing the light. Each chemical element leaves a distinctive pattern of lines in the spectrum. By analyzing these patterns, astronomers can determine which elements are present in the stars and estimate their ages. The motion of stars within the galaxy can also be inferred through spectroscopy. When stars move toward or away from Earth, the wavelengths of their light shift slightly due to the Doppler effect. Measuring these shifts allows astronomers to estimate how quickly stars are orbiting within the galaxy. These measurements reveal how much mass must be present to hold the stars in their observed orbits. If the stars move too quickly for the visible mass alone to contain them, additional unseen mass must exist. Astronomers also observe the hot gas filling the cluster surrounding IC 1101. This gas emits X-rays that can be detected by orbiting telescopes. The distribution of X-ray emission reveals how the gas is shaped by the gravitational potential of the cluster. Another powerful technique is gravitational lensing. When light from distant background galaxies passes near a massive cluster, the gravity of the cluster bends the light slightly. This bending distorts the images of those background galaxies. By measuring these distortions, astronomers can map the distribution of mass within the cluster, including both visible matter and invisible dark matter. These maps confirm that clusters like Abell 2029 contain enormous halos of mass extending far beyond the visible galaxies. Computer simulations also play an important role. By modeling how galaxies merge within clusters over billions of years, astronomers can compare simulated structures with real observations. When the simulations reproduce galaxies similar to IC 1101, they provide insight into the processes that built the system. Through these combined methods, scientists gradually assemble a picture of the galaxy's structure and history. Each observation contributes a piece of evidence that helps clarify how such a massive galaxy formed. Although no single measurement reveals the entire story, together they create a coherent understanding of the system. Astronomy often works this way. The universe cannot be manipulated directly in laboratory experiments, so its history must be reconstructed from the signals that reach our telescopes. The faint light from IC 1101 carries with it the record of billions of years of cosmic evolution. The visible stars of IC 1101 represent only part of the galaxy's total mass. In fact, most of the matter associated with galaxies is invisible. Astronomers refer to this unseen component as dark matter. Dark matter does not emit light, absorb light, or reflect light in any detectable way. If it were floating in front of you in space, it would remain completely invisible. Yet its gravitational influence can be measured through the motion of stars and gas. In spiral galaxies like the Milky Way, astronomers notice something unusual when measuring the rotation of stars around the galactic center. According to the gravity produced by visible matter alone, stars far from the center should orbit more slowly than those closer in. Instead, observations show that stars in the outer regions move almost as quickly as stars near the center. This behavior suggests that additional mass surrounds the galaxy, extending far beyond the visible disk. This unseen mass forms a vast halo enveloping the galaxy. The halo contains far more mass than the stars themselves, providing the gravitational framework that holds the galaxy together. For a giant galaxy like IC 1101, the dark matter halo is likely enormous. Its visible stars form only the luminous core of a much larger gravitational structure. The halo may extend tens of millions of light-years into space, far beyond the region where the galaxy's stars are concentrated. Within this halo, the gravity of dark matter influences the motion of galaxies throughout the cluster. Clusters themselves are embedded in even larger halos of dark matter. These halos help bind hundreds of galaxies together into a single gravitational system. Without dark matter, structures as large as galaxy clusters would have difficulty forming in the time available since the beginning of the universe. Ordinary matter alone would not have been able to clump together quickly enough under gravity before cosmic expansion spread it apart. In modern cosmology, dark matter provides the scaffolding on which galaxies and clusters form. Shortly after the Big Bang, tiny fluctuations in the density of dark matter began to grow through gravitational attraction. Gas composed mostly of hydrogen and helium gradually fell into these dense regions. As the gas collapsed, it formed the first stars and galaxies. Over billions of years, these early galaxies merged and assembled into the large structures we observe today. The dark matter halos surrounding them continued to grow, guiding the motion of matter along the filaments of the cosmic web. IC 1101, therefore, exists not simply as an isolated object, but as part of a vast dark matter framework extending across the cluster and beyond. The galaxy we see glowing faintly through telescopes is only the visible tip of a much larger structure composed primarily of invisible matter. Understanding this hidden framework is essential for explaining how the largest galaxies in the universe can exist at all. The dark matter halo surrounding IC 1101 does not exist in isolation. It connects to the larger network of matter that spans the universe. When astronomers map the distribution of galaxies on the largest scales, they find that galaxies trace out long filaments stretching across hundreds of millions of light-years. These filaments intersect at dense nodes, where clusters of galaxies form. Abell 2029 sits at one of these nodes. Matter flowing along the surrounding filaments gradually accumulated in this region over billions of years. Galaxies formed along the filaments and drifted slowly toward the cluster center under the influence of gravity. As they moved inward, some became satellites orbiting within the cluster. Others merged with neighboring galaxies along the way. The central galaxy of the cluster benefited most from this flow of matter. Positioned at the deepest point of the gravitational potential, it became the destination for galaxies arriving from multiple directions along the cosmic web. Over time, these infalling galaxies added their stars and gas to the growing system. The central galaxy expanded outward, incorporating the remnants of its neighbors. This steady supply of material explains how galaxies like IC 1101 can grow to extraordinary size. Their position within the cosmic web places them at crossroads, where matter converges. Clusters located at these intersections experience particularly strong growth because multiple filaments channel material toward them. The galaxies residing at their centers therefore accumulate mass more rapidly than galaxies in quieter regions of the universe. The cosmic web thus provides the large-scale environment that shapes the formation of giant galaxies. It acts as a network of invisible highways, along which matter travels over cosmic time. IC 1101 occupies a privileged position within this network. Its location allowed gravity to gather material from a vast surrounding region and assemble it into one enormous galaxy. The visible galaxy is therefore the luminous expression of a much larger process, unfolding across millions of light years. Through the combined influence of dark matter, galaxy mergers, and the flow of matter along the cosmic web, the universe gradually constructed one of the largest galaxies ever observed. The next step in the story moves beyond structure alone and considers what this enormous system reveals about the limits of cosmic growth. If you'd like, I can now write Cluster D to 2,000 words, which will conclude the script with Cosmic Limits on Galaxy Size, Time Perspective, Ancient Light, Future Evolution of the Galaxy, Final Philosophical Closing in QSJ tone. The existence of a galaxy as large as IC 1101 raises an important question about the universe itself. If gravity can assemble structures on this scale, could galaxies grow even larger? Or does the universe impose limits on how big a galaxy can become? The answer lies in the balance between several competing processes. Gravity pulls matter together, encouraging the growth of larger and larger structures. At the same time, the expansion of the universe steadily stretches space, carrying distant regions farther apart. Dark matter also plays a role in this balance. Its gravitational influence shapes the large-scale structure of the universe and determines where matter gathers most efficiently. Regions where dark matter concentrations are highest tend to produce the largest galaxy clusters. Inside these clusters, the process of galactic merging can continue for billions of years. Smaller galaxies drift toward the cluster center and gradually become part of the central galaxy. Each merger adds stars, gas, and dark matter to the growing structure. Yet this growth cannot continue indefinitely. As clusters evolve, the supply of nearby galaxies gradually diminishes. Many of the galaxies that once orbited the cluster center have already merged with the central giant or moved into stable orbits farther away. At the same time, the expansion of the universe slowly increases the distances between galaxy clusters. Material that might once have fallen into the cluster becomes less likely to reach it as cosmic expansion accelerates. These combined effects mean that even the largest galaxies eventually approach a kind of equilibrium. Their growth slows because the environment around them no longer provides a steady stream of new galaxies to absorb. In this sense, IC 1101 may represent something close to the upper range of galaxy size that the universe commonly produces. It sits in one of the richest cluster environments known, positioned at a gravitational crossroads where many galaxies once converged. Under those conditions, gravity had both the time and the material necessary to assemble a galaxy on a truly enormous scale. But even this giant cannot grow forever. Its history reflects the balance between gravitational attraction and cosmic expansion that shapes the entire universe. When astronomers observe IC 1101, they are not seeing the galaxy as it exists today. The light reaching Earth from that system began its journey more than 1 billion years ago. Light travels extremely fast, covering about 300,000 kilometers every second. Even at that speed, crossing the distance between Earth and IC 1101 requires more than 1 billion years. This means that the image recorded by telescopes is a snapshot from the distant past. While the light traveled across intergalactic space, the galaxy itself continued evolving. Stars within the galaxy completed orbits around the center. Some massive stars ended their lives in supernova explosions. Others collapsed into neutron stars or black holes. New mergers may have occurred as additional galaxies drifted toward the cluster center. Gas clouds may have compressed and formed new stars in localized bursts. From Earth, we cannot yet see those changes. The information about them has not had enough time to reach us. Astronomy therefore operates as a kind of cosmic archaeology. Each distant object reveals an earlier chapter in the history of the universe. The farther away we look, the further back in time we see. Nearby stars appear almost as they exist today. distant galaxies show us what the universe looked like billions of years ago. In the case of IC 1101, the light we observe left the galaxy long before complex life appeared on Earth. At that time, our planet was inhabited primarily by microscopic organisms living in ancient oceans. While evolution unfolded slowly on Earth, photons from distant stars were traveling across the vast emptiness between galaxies. Those photons eventually reached the telescopes that allowed astronomers to discover and study the giant galaxy. In this way, the observation of distant galaxies connects our present moment to events that occurred long before our species existed. Every image of the deep universe is also a record of cosmic history. Although IC 1101 appears enormous and stable, its future will continue to unfold over extremely long timescales. Galaxies evolve gradually as their stars age and as the environment around them changes. Most of the stars in IC 1101 are already quite old. Many of the massive stars that once illuminated the galaxy with bright blue light have long since ended their lives. What remains are smaller stars that burn their nuclear fuel much more slowly. Stars similar to the Sun will eventually expand into red giants before shedding their outer layers and leaving behind dense stellar remnants known as white dwarfs. This transformation may take billions of years. Even smaller stars, known as red dwarfs, burn their fuel extremely slowly and can continue shining for trillions of years. These stars will become the last sources of visible light in the distant future of galaxies like IC 1101. Eventually, the supply of cold gas needed to form new stars will become increasingly scarce. Without fresh gas collapsing into stellar nurseries, star formation across the galaxy will gradually slow. Over immense periods of time, the galaxy will grow dimmer as more stars exhaust their nuclear fuel. Stellar remnants such as white dwarfs, neutron stars, and black holes will dominate the population. The supermassive black hole at the center will remain one of the most enduring objects in the galaxy. Its gravitational influence will continue shaping the motions of nearby stars. Yet even black holes are not eternal. According to quantum theory, black holes slowly lose energy through a process known as Hawking radiation. Over unimaginable spans of time, they gradually evaporate. For a black hole containing tens of billions of solar masses, the evaporation process would require far longer than the current age of the universe. Nevertheless, the laws of physics suggest that even these enormous objects will eventually fade away. The giant galaxy we observe today, therefore, represents only one phase in a much longer cosmic story. When confronted with the scale of a galaxy like IC 1101, it is natural to feel that human existence occupies a very small place in the universe. 100 trillion stars, spread across millions of light years, make our own planet seem insignificant by comparison. Yet the existence of such enormous structures also reveals something profound about the nature of the universe. The same physical laws that govern the motion of stars in IC 1101 operate here on Earth. Gravity shapes the orbits of galaxies just as it guides the fall of an apple from a tree. The nuclear reactions powering distant stars rely on the same atomic processes that occur within our own sunday. Even the atoms that form our bodies share a connection with distant galaxies. Elements such as carbon, oxygen, and iron were forged inside ancient stars that lived and died long before our solar system formed. Those elements were scattered through space by stellar explosions and eventually became part of the cloud of gas that collapsed to form the Sun and its planets. In this sense, the history of galaxies is also the history of the matter that makes up life itself. The processes that assembled IC 1101 from smaller galaxies are part of the same cosmic evolution that produced our own Milky Way. Long streams of stars in the night sky reveal that our galaxy is still absorbing smaller companions even today. Billions of years in the future, the Milky Way and the Andromeda galaxy will likely merge to form a larger elliptical galaxy. That future galaxy may resemble the kinds of systems we see today at the centers of galaxy clusters. IC 1101 therefore represents an extreme example of a process that occurs throughout the universe. Small structures combine to form larger ones. Galaxies grow through mergers. Clusters gather galaxies together through gravity. Over time, the universe builds increasingly complex structures from the same basic ingredients. Our own existence is connected to that process. The atoms that form living organisms were created in stars. The planets on which life emerges form within galaxies shaped by cosmic evolution. When astronomers observe distant galaxies, they are not simply cataloguing remote objects. They are studying the history of the universe that ultimately produced the conditions necessary for life to exist. The discovery of enormous galaxies, such as IC 1101, reminds us how far cosmic evolution can proceed when gravity and time work together. It also reveals something remarkable about the ability of human curiosity to explore the universe. From a small planet orbiting an ordinary star, astronomers have learned to interpret faint signals traveling across billions of light years. By analyzing those signals carefully, they reconstruct the structure and history of galaxies far beyond the reach of any spacecraft. In doing so, they expand our understanding of the cosmos and our place within it. The largest galaxy ever discovered is not simply a record of extreme size. It is a window into the processes that shape the universe on the largest scales. IC 1101 formed in the center of a massive galaxy cluster, where gravity gathered matter for billions of years. Repeated mergers with smaller galaxies gradually expanded its structure until it reached a scale measured in millions of light years. Its stars preserved the chemical signatures of many earlier galaxies that once existed independently. Its central black hole reflects the long history of mergers that brought mass into the core of the system. The galaxy itself sits within an enormous halo of dark matter connected to the larger network of the cosmic web. Through that network, matter flowed toward the cluster center over cosmic time. Although the galaxy appears stable today, it continues to evolve slowly as its stars age and its environment changes. Like all cosmic structures, it represents a temporary stage in the long history of the universe. From our perspective on Earth, the light from this giant galaxy arrives as a faint signal after traveling more than 1 billion years through space. That light carries with it a record of cosmic growth, revealing how gravity assembled one of the largest structures ever observed. In studying such distant systems, we gain not only knowledge of the universe, but also perspective on the processes that shaped our own galaxy and ultimately our own existence. The largest galaxy ever discovered stretches far beyond ordinary imagination. Yet the ability to understand it began with careful observations made from a small planet orbiting an ordinary star. If you enjoy exploring the universe from this perspective, consider subscribing to the channel. New videos continue examining the structure of the cosmos, from distant galaxies to the deepest scales of space. And if you would like to continue the journey, another exploration of the universe is waiting for you now. And that quiet act of observation continues to expand the boundaries of human knowledge.